Thank you for the introduction. Okay, yeah, so I'm talking today about multimedia fun. Fun is like fun for coders, so not actual like jokes or anything. And yeah, I was already introduced. I'm hosting Bitluni's lab. I'm doing that full time, and yeah, behind the goofy faces, there's quite a lot of actual valuable content, probably. And I hope you enjoy it as well. If you don't know my channel yet, please check it out. Okay, so I have like 60 slides, only 30 minutes, and I planned like 1 hour, and I have only 30 minutes to talk. So let's do it quick. Who of you knows the ESP-32? Okay, everyone. So you don't need that much introduction into that one. So it's a successor of the ESP-8266 and 32-bit processor, dual core, and has an additional core. So it's a 3-core. So this ultra low power coprocessor. It's actually a 3-core system on chip, and the main cores can go up to 240 megahertz. That's quite quick, so you can do a lot of stuff on that. And we got an Arduino extension, so in the boards manager you can add like a link and use it with the Arduino IDE. So it's quite convenient to get started with that. And there are some key features that are outstanding as a microcontroller. So we get like 520 kilobytes of SRAM, and that's quite a lot. That's a lot more than every other microprocessor that you can get, and that in this price range. And what we have at the end is like 200 kilobytes left in the Arduino, because we have like only 360 for data. So the code is like loaded from the flash into a portion of the RAM. So, and there's a Bluetooth stack and Wi-Fi stack, and we have like 200 kilobytes left. And we can work with that, so there's plenty of room for frame buffers. And we get a ton of peripherals, and two of the most interesting ones for us is right now the two I2S channels, and they have DMA capabilities, of course, and two digital to analog converters that are built in. So let's talk about I2S and DMA. It does the data transfer without any CPU, so you can just set it up and it will do its work in behind the scenes. And you can achieve with that like 32-bit samples, like 10 mega samples a second, 16-bit like twice as much, and up to 40 mega samples a second in the 8-bit mode, which is only available, unfortunately, in the second channel. And yeah, we have two modes, serial and parallel mode, and we can directly access the digital to analog converters using the first channel. We have also the convenience of using GPIO matrix to connect like any output of the I2S, like the parallel data lines, to any output pin on the microcontroller. So let's talk about the bandwidth a bit. We need to set up a clock. So this is how like the block diagram of the clock looks for the I2S. And we take like two different clocks, and PLL divided by 2 is like the main clock, which is 80 megahertz. And that's divided by 2, we get like 40 in, and then you have like nasty dividers here, and you usually don't want that. So why should I divide it, the clock? I need plenty of power and plenty of speed. So we want to get this as low as possible. So unfortunately I didn't tell that. For video we need like 12 mega samples. So like this, okay? Sorry, I was confused for a second. And so we want that clock to be really fast. So, but I will talk about that in a moment. So what do the analog digital to analog converter do? They convert like simply digital values to analog voltages. So we get like between 0 and 3.3 volts anything we want, and we can use like 8 bits because the built-in decks are 8 bits. And usually they are like implemented on resistor ladders, and they have like an additional buffer, so like an op amp to get like good impedance or something. So what let's talk about audio. So let's start with that. We have 2 digital to analog converters, and we can do like stereo on that. And we can do that also without I2S. We can access them directly via registers. And what has been done with that is like internet radio already by other people and MP3 player, but I will not show that here because I want to show my stuff. And so I did like a super simple AM radio broadcast. We have like a super fast I2S output with digital to analog conversion. And I did also like implementation of like a sound engine that I show certainly, and you can use that already to like play waves and synths and so on. We haven't used that much but I have several projects that I might show. So let's start with the AMA radio. So it's quite simple. I hope that plays. Yeah. So simple setup. We have here this jumper wire. That's our antenna, and I connected even the probe. So yeah, the length of the antenna isn't that long, but the distance that we have to get to the receiver is not that far as well. So that should work. And so you can see this is our base frequency of 800 kilohertz around. And then we can do a lot of stuff, like small gadgets.
This is an emergency broadcast. Nuclear missile inbound detected. Seek shelter, duck and cover.
Yeah, or troll grandmas or something. So, yeah, quite neat project. You just need to connect the wire to a pin, and you have an AM radio transmitter. So another project that used sound, and in this case, I used the I2S only for the RGB LEDs, but we will get to that later. And we just take that's a lightsaber. So when you wield it, you want that cool wielding, that noise, that hum. And we can take like gyroscope input and take the angular velocity and synthesize like a cool hum that's actually synced with what you're doing. So so the engine looks like that somehow. So the timer just writes the digital to analog converter and takes like the samples from the mixed buffer. And we have like sound objects that playing at their speed. But we can also put in like a simple object that we can implement and do like synthesis inside of it. So I just used like Audacity and took like a hum from the movie and analyzed which major frequencies are appearing in this, and I just take the base frequencies and yeah, and then like the simple class just takes the sound engine takes the next sample, and this is simply synthesized in here. So this is a basic synthesizer, and what we get in the end is like this lightsaber. Yeah, so yeah, I did that for Electromaker, so this is unfortunately not on my channel, but it was nevertheless one of my coolest projects, I think. So we had like, when turning it on, it was like a sample plate, and turning off, it was also a sample, but the wielding sound was actually synthesized in real time on the ESP-32. So you probably we're thinking, okay, yeah, you use like the timer and 22 like kilo samples a second. That's like you call it quite often, and you have to do that like that. It's maybe taking too much power or interrupting too often. So I tried. So maybe we can utilize this ultra low power coprocessor. Yeah, it has like 4 kilobytes of RAM that you can use for data and code, and you can access this directly from the other cores. And I thought, okay, maybe we can yeah, the actual frequency of that core is 8 megahertz, which is quite fast. So that was like an older 80 tiny in full speed. So, but we have to, it's around 8 megahertz, so we have to measure the actual frequency, but actually the API gives us the functions to do that. So we can, while initializing it, we can measure the actual frequency of the coprocessor, and then we can set the delays in the code of the coprocessor to match our actual frequency that we want to have. So we want the coprocessor to put out the samples at the rate and an actual rate of 22 kilohertz or something. So, and that's actually achievable. The instruction set is really low, but you can access the DAC registers. But yeah, unfortunately only with fixed values, so you can't load like a byte from a buffer and write it to the DAC. You have to write like a certain value. So, but okay, yeah, we can work with that. We just make a huge switch. Yeah, that's in C++, but we did it in assembly, so I wrote like generator like with a loop, the assembly code that actually writes 0, writes 1, and then after that always a jump back. So we have like a jump to the, we can calculate the offset, jump there, write the value and jump back. So yeah, that takes a lot of our 8 kilobytes, but still we have like 4 kilobytes left for our samples, and then yeah, that's quite cool, because then we don't have to like use the interrupt for like 20,000 times a second. We can just let the ultra low power processor act like a small sound processor. So how about video? Yeah, sure. Can we do digital video with the ESP-32? Yeah, TFT displays have been done. That was one of the first example projects, and even I2S has this LCD mode. So the parallel mode is called LCD mode in the documentation. So that has been done. I don't have to cover that. And how about DVI, HDMI? Ooh, yeah, that gets hard. I would say no. But I also said that about PAL color, and actually it worked after all. So yeah, but it's quite hard to achieve. You have like a differential TMDS signal with the lowest resolution of VGA needs 25 megahertz, and this times 10 bits, since this is a serial protocol, so you would need like 250 megahertz clock on that. So that's unfortunately not achievable, since the GPIO matrix of the I2S works only with maximum of 40 megahertz. Okay, yeah, okay, LED matrices, we can do that. So we can use simply Neopixels. We have seen this in the Lightsaber project already. And yeah, I call it the serial Morse protocol. So Charles have shown that before. And we can use I2S serial mode for that, and the DMA transfer assures a perfect timing. So with the real-time operating system of the ESP-32, we get often problems with the timing, since it's like task-based system. But the transfer via DMA assures we get like the actual timing that we need, but we also need the gamma correction. That's really important if you want to display like actual images, because then you get like nasty color shifts. You have like a lot of red and a little bit of blue and a little bit of green, but the little bit of blue and green is so bright you get like pink instead of red. So you need that gamma correction. And yeah, how do you do this? So Charles, that's a little bit familiar, isn't it? If you have seen Charles talk before on LUTs, yeah, that's actually what I did as well. But I did like, that's 32 bits wide, and I have like it's like 256 values, so I convert directly RGB or BGR or always this confusion. I convert it and then write the bytes. And the gamma correction, you can even count that in that loop, but that's an older implementation that didn't have that yet, but my LED wall did that. So let's take a look how that looks. So you can do procedural graphics that works nice, that are 1.2K addressable LEDs, and you can even use like an ESP cam and transfer via UDP packets the video from another ESP over Wi-Fi. It's a little bit choppy, but it works. Okay, the beamer doesn't show it well, but yeah, you can transfer video and display it on the LED wall. So that's great. So that's how we covered digital video. Okay, let's try the analog video now. And that's the interesting. Simple vector display on the oscilloscope, old school, and it's super cool. You have to do that. We will. Then we can do composite video. That works as well. I didn't manage to get NTSC color running, so you have to take Charles' code then. But we can also do VGA. That's a little bit more problematic since you need 3 digital to analog converters for the 3 color components. But we can do that with external resistor ladders, or we can just use 1 bit per color component. So yeah, as mentioned, Charles did that on the ESP-32, which was super impressive, and I just understand how he did that yesterday when he did his rehearsal, and I was surprised that it's quite similar to what I did at the end. So let's take a look first at the vector display. So if you have like a super old school analog oscilloscope, keep it. Yeah, they're doing really good graphics. I don't have a video on old oscilloscope. I forgot to somehow take it with me, but I can show some footage of digital ones. So you connect the probes, super easy. GPIO 25 and 26 are the digital to analog converters, and you set your scope to XY mode. Okay, yeah, that's what we did. And then you can use on digital scope, you need a trigger because then you get like your display frames will be like shifted, and it doesn't look good, but you can use a trigger. You can simply send like on X or Y, you can use like a high value and use that actually as a trigger. So you can have the start of your frame. Then you need like to set the memory depth so to a lower value, not high memory values that don't work well with digital scopes as a vector display. And you need to set up your time frame, and then actually, yeah, duration equals brightness. So if you keep a point at one, send a point repeatedly, it will get brighter, even on the digital scope. So what do you do when you have like a graphics system implemented? Yeah, you do a like 3D engine, yeah, or even a camera input. So back then the cameras, that was one of the cheapest ones. Now you have ESP cam, which is a super cool module. Yeah. So let's take on a short video on that. So real time. Yeah, you can use a scan of yourself that you have done with Kinect. So like display a point cloud. Here, that's also a point cloud of some Stanford, and even like wireframes. It doesn't look that well on that scope. Yeah, but real-time camera input, yeah, that works really great. I was surprised of that as well. Yeah. Okay. Yeah, that was the old school one. Now we can do NTSC and PAL, and that's a long topic. So we need only one wire for that. All the video comes through one wire, and we have like color frequencies that we have to modulate, and that is the PAL frequency. I don't know which is the NTSC. I didn't write it down, but then we have some like grown features. So over time we have like interlacing. Then we have to do like the horizontal sync, then color burst, and plenty of awkward stuff. Like for the vertical sync, we have like half lines. So what is that? So let's just start taking a look at the line. So this is like 64 microseconds, and we have like the sync signal that's voltage level 0, and then we have like black that's around 0.3 volts, and then we have the gray values. And then we have a blank phase. So this is the visible area. And yeah, the vertical sync is a little bit more complicated. You can see up there are some pulses, and down there, and there is even half a line somewhere there. I can see that, but you have like, since these are the two fields of this nasty interlacing, you have to shift like half of the line to get it like interlaced, and they did it like very, very, very awkwardly. Okay, so to achieve video, we have to go beyond the API, since you can't set the I2S clock to higher than 1 megahertz from like the API calls. The technical reference manual is your friend. It's really, I love it. The 669 pages, I didn't read all of them, but the pages, it's really well written. It's so much documentation. It's so good. It's more documentation than the total I made in my complete career, including university and school. And so yeah, it's quite impressive, and I love it. So. But you also don't trust the limits they write down there. So, but if you go over the specification, you have to try this. I dodged a bullet with a board that I sold, where in my library I use like higher frequency, but then it works on half the modules, and then I got like one. It was simply black. I didn't see any video, and that was. But I could simply update the library, and that worked fine. Yeah, so one example is this divider. We had this before, and we want this not to be like a high value, since our clock will be divided by high value, and the manual says whose value is higher or equal to 2, but actually you can write 1 and it works. So do it, try it. So if you trying something and just take other values that are probably, it might work. So yeah, do it. It's quite simple. We have the clock set, and we need like just fill half a line of buffer with the syncs and the video. Then we simply take the buffer and enqueue it to I2S using the API call. That's super simple, and it works for this case, and simply repeat. So this is how it looks like. We just connect to GPIO 25 and ground, and let's take a look at the video. So yeah, you create it's old school, and you create obviously like a 3D engine. Yeah, that works nice, 50 frames per second, and a lot of triangles, a lot, like 90s, a lot. And yeah, but something is missing. We need audio. So we have one digital to analog converter that we use with 13.3 megasamples. That's a good value, since it's like you have the base clock of 18 megahertz that I used, and that's like a part of that you get not like you get a clean clock without any jitter, and your pixels are fine. So, but we have an additional digital to analog converter, and we want to use that for audio. But we don't want to oversample like 13 megahertz audio. No, we want to use like 20 kilohertz. We can actually not do this. So both digital to analog converters are using one clock. But I read the documentation. You won't find this anywhere in the API. So there are certain modes that you can set for the FIFO, and you can set it such that one channel will be taken from the data input, and one channel will be taken from a single data register. And you can write that register anytime you want. So we take our sound engine, do like a timer call, and set that single data value, and the FIFO will simply take every like 13 million times a second will take simply the single data value and write it to the digital analog converter, and it doesn't matter how often we update it. It will simply work, and actually it does work. So yeah, you simply need two controllers, and then you get like, yeah, you create like recreate Tetris, but you update the Buran to a newer like Falcon Heavy start and some booster landings and a flyby of the Roadster to Mars. So yeah, and then you can like take a small CAT from an intercom and create like a small retro Game Boy that's even more retro than the original one. It's a little bit chunky, yeah, but it works. Well, but it draws some power, yeah. Okay, so how about color? Okay, yeah, I didn't get NTSC working, so use the ESP-32 and Charles Lohr's code. Check out his talk on that from before. It's on YouTube, so you can watch it if you didn't see it. Yeah, but I took over PAL, and I'm from Europe, so that's obvious. That's a good choice, and yeah, we have used 13.3 megasamples a second, and we have a color carrier of 4.4 megahertz, and that actually aligns quite good. So you get like almost perfect three samples per pixel for the color carrier. Yeah, but our digital to analog converter at 13 megahertz, this is a square wave according to the digital to analog converter. Yeah, so. I don't know if we can get a clean, get a clean signal there that's recognized by a TV. So what we want is a signal like that. So that's a like perfect sine wave, and what we get with our 13 mega samples on NTSC color carrier is something like that. Yeah, okay. But what we get on PAL is that. That's pretty good, isn't it? So it's a little bit shifted from here to there, but it works fine. So that's probably why PAL works. But yeah, what do we need for PAL? YUV color space? Oh no. Yeah. Then quadrature amplitude modulation. What is that? And phase alternating line. Okay, let's take a look what's quadrature amplitude modulation. Yeah, I'm not an electrical engineer. I'm sorry, I don't know that. I didn't have signal theory. Let's just take a look in Wikipedia. It shouldn't be that hard. Oh, okay. Yeah, so this is the point where where I would give up. But actually, if you browse the web, you find some additional information, and just use this formula. So this is one line, this is the second line, and E is like the energy. So that's your amplitude or whatever. And there's Y, there's U and V, and sine and cosine, that's like fixed for every pixel in the line. So that's it's the burst signal, and you have the time, and that's multiplied by a factor that gives you the color carrier. So that isn't very complicated if you write it down like that, and maybe do like a JavaScript emulator to do that. So you can check this out on my page. I did this to try to understand how this actually works, and you can even introduce like an error, since you have like a compensation in PAL. It compensates between the two lines, and the error cancels out, and you have like, here is the shifted color, so this would be the hue is completely off, but this correction does a quite good job. So it's way better than never the same color. And yeah, so that was how I more or less understood how it's working, or was convinced, okay, that could work. So is it good enough? Yeah, we need a frame buffer, and I use like YUV. Y is like the brightness. So for each pixel, I have like 4 bits for Y and then a color component. Since we have this alternating line, then the resolution of the color is vertical is half anyway. So I just write V and U alternating between the lines. So we can use like for 1 pixel, 1 byte. And that fits in our memory. And then I use like for conversion between RGB and YUV, I just use a lookup table. And then, yeah, can we do this 13 million times a second, this calculation? So, yeah, I hinted you off that these both values are constant, and then you have just only addition and multiplication. Yeah, sure, you can do that. And that utilizes 1 core 100%. You do this quadrature amplitude modulation using lookup tables and this multiplication as fixed point arithmetic. So that works, and this is the code. Yeah. So this is the inner loop. You see there are plenty of LUTs, so I'm actually really calculating this modulation, and we get a lot of color options there. But yeah, you have the awkward word packing that you have swapped the byte order for I2S buffers. But yeah, I tried to optimize this code, and I thought, okay, I will do like this and that, and I tried like for hours, and every time I just swapped two instructions, and it broke. So this is really the optimum code in C++ to do this. Anything else won't work, at least for me not. I didn't find any permutation of code that works except for this one. So yeah, but we can simplify further. So non-interlaced PAL, that interlacing is so nasty, we want to get rid of that. So game consoles of the 90s have used that already. So you simply send over the first field over and over again, and you get your frequency is a little bit off. It's not 50 hertz, it's a little bit more, but yeah, you can get rid of this half line that you have to send, and you get 50 frames per second, half the vertical resolution. We don't have a big frame buffer anyway, so that's what we go with. And the final code is only 180 lines of code, and it's even, I think I even published it under public domain. So yeah, let's take a look at what we got. Yeah, and we don't need any components. We can just take like some connectors. Yeah, okay, we can take like a capacitor to get rid of the DC offset for the audio. And we can simply build a simple console for like dev kit, and we have a simple console like that. It works very good on TFT, and it's super quick. The ESP, you have still 1 core, then we can do a lot of stuff on that. And you could even do it like that without that capacitor, since most of the amplifiers will take care of this DC offset anyways, and you get even better bass. So yeah, but there is a slight problem with the digital to analog converters are very delicate. You never short them with like the 3.3 volts. They will break. So I have like a box full of ESP-32s with broken one or the other digital to analog converter. So the conclusion of this is we have ton of peripherals, but there is one missing here. Yeah, we can add this. It's just a driver. So I implement driver, you don't need an extra hardware, and that works nice. Yeah, but we have some drawbacks. We utilize 1 core completely, and yeah, we don't have enough memory for a ring buffer where we would like let the I2S send the frame over and over again. We just change the pixels. yeah, the problem is we need like 3 samples per pixel, and then we have this factor of 2. The problem is we can use on the first channel where the digital to analog converters are fixed to, we can only use 16-bit mode there. So the DACs are 8-bit, but yeah, we waste like half of the memory to because it's not possible to send 8-bit data on that. So, and we don't have like 500 kilobytes of memory to do it without recalculating every single line. Okay, yeah. You get also problems with the Wi-Fi since the core also takes care of the Wi-Fi stack. The Wi-Fi works, but then your frames will drop out and the signal is desynced and so on. And yeah, YUV, oh yeah, you don't want to do this since if you like write a game and you want to do some blending and you have like an alpha channel, I cheat there. I simply take the Y component and do like blending with the Y component, and I just ignore the color. I just take the last UV components. That works okay. But yeah, how about VGA? Yeah, resistor ladders. Yeah, external digital to analog converters. We have the parallel I2S that we can simply route to any GPIOs, and yeah, we just add to external DACs, and yeah, we have 5 signals for the VGA, R, G, and B, analog signals for the components. And then we have a horizontal sync, that's a digital signal, and a vertical sync. So, and yeah, we can use with the I2S, we can use like a 16-bit mode and 16 bits per pixel. We reserve, of this 16, we reserve 2 bits for the sync signals, since these are digital, and take the other 14 bits for the color components, and we simply store the sync signals in the frame buffer as well. So this is how it looks like. Okay, I'm almost finished. Okay, it's like 13 more slides. It's not much. No, so we get like high color-ish. Yeah, it's only 14 bits, but it's good enough, I would say. Short introduction to DMA buffers, since yeah, we don't get along with the API functions anymore. We want the real deal. We just initialize the DMA buffers ourselves, and the DMA buffers, they work with descriptors, so that's all like small like structures that have pointers to data buffer and a pointer to the next descriptor. So, okay, I'm not sure about this anymore since I talked to Sprite about that. Yeah, and but you have only 4 kilobytes per buffer, so you have like to chain multiple buffers to get like your data sent, and the buffers have always been in DMA memory. That's how they call it, and that DMA memory is actually SRAM. Sorry. Yeah, it's good. Cool. So this is SRAM. PSRAM doesn't work. That's too slow, and it's fetched over SPI. So, and that's even too slow to be used like 50 frames a second, like this high bandwidth. Then yeah, that's I'm not sure about this anymore, since Sprite wasn't aware of this as well. But yeah, there are certain rules, but we can set up a ring buffer. So we can store a complete frame in DMA memory, and simply we have like the sync signals and maybe black lines which aren't visible, and we can like only initialize one black line and one sync pulse, and then multiple descriptors just point to that single one. And so you can save a lot of memory on that, and you can use cropping to reduce your memory consumption, like nice wide mode, but you only saving memory. And yes, you let the last descriptor just point to the first one, and let the I2S run, and it will run forever. And you only just update the frame buffer, and the processor is free to do anything you want. So yeah, that's quite good. how do we do that? Resistor ladders, external ones. I don't even have a buffer at the end. I simply write this, I connect this directly to the VGA cable, and I have like a trimmer resistor here to get the right voltage level. That works good enough. So it's a little bit messy on the breadboard, and let's take a look what the result is. Yeah, it's really crisp. So the pixels are much nicer than with PAL. And I also wrote like a library, so you can, and we can do real-time ray tracing since we have now 2 cores for our purposes. So we get like 6 frames with reflections, shadows, and so on. Only like 3 primitives, but yeah, okay, that works. So that was so nice, and I wanted to make it available to everyone, and I wrote like a library. Yeah, you probably hate the ESP-32 lib name, but I want to include the sound and PAL implementation as well in this to just, since I don't like to have like ton of different libraries that I have to include and update and so on, I will just maintain one library that has all the good stuff. And I wrote also a wrapper for the Adafruit GFX library, so you can just take it and use it with your old projects. It will work. You can simply display it on an old VGA monitor that everyone is throwing in trash since they don't have HDMI or something. So yeah, a bummer. So we have 8-bit is missing on the first channel, and yeah, the internal DACs, we could use PAL with 8-bit mode, and we would have like the same ring buffer for PAL, but yeah, it's unfortunately not possible, and that first channel would waste like 50% of the memory and bandwidth. But I talked to Sprite, and he actually opened like an issue, and they will probably change that in like not the next one, but the next after that. So we probably will even have like PAL in the future without utilizing a core completely. And what we can do with this 8-bit mode is we can use like 2 bits for color component, and we have like the sync signals at the end. And we can get, with the 40 mega samples, we can get up to 800 by 600 resolution. But we don't have enough memory for the frame buffer. We can do like cropping, but we can also use an interrupt to fill each individual line like on the fly with procedural graphics or like some compression. I did even decompressing like run length encoding in the interrupt, so that simply draws and fills the buffer. So, is this a video? Is it missing? No. Oops. Oh yeah. So this is how the 8-bit mode looks like, and this is a high resolution. There is free memory, 30 kilobytes left, and yeah, and you can use also text mode. Yeah. And okay, let's make it quick. You can also use VGA without extra components. You simply use 1 bit per color component and have like only like 3-bit graphics. So we have the comparison here. It doesn't look so good anymore, but yeah, this one actually does. So you can take it. So what is our conclusion for that? Yeah, ESP-32 is a beast. You can do audio, video, obviously, and you can use 1 core as a GPU. Cool. And the memory is crucial. So I was asked quite often, why don't you use the STM32? Yeah, there are STM32s that have like 512 kilobytes, but yeah, they're a lot more expensive and have like 1 million pins and are huge. But the ESP-32 does it very well. So for anyone who's designing microcontrollers, please put in like maybe 640 kilobytes. That's enough for everyone. And we can do frame buffers and graphics. And you can build like for $7, you can build a game console, including the controller from AliExpress, obviously. So what's the future? You can follow my journey. This was like 3 years of my life. And you can follow my journey on my channel. Yeah, I'm building like a mini computer, and I'm trying to optimize the console a bit more. And you can follow me on Twitter, YouTube, and maybe my page or GitHub, or check out from time to time. I have even stuff on my Tindy store, and I want to thank you for your attention.